styles or stages of our network environment, and how we have excelled from in order to process the data in a more efficient way, and in order to collect sense the environment, and in order to process our applications in a better manner. uh, so how what are the different stages that we go through during the past decade, and finally we will arrive at fog computing and IoT, and what are the benefits of using these two technologies. Firstly, starting with the major stages of network information system. We started back there. Then we started from mainframes. We used to have dumb terminals out there, and those dumb terminals take the services or utilize the services of the surrounding of the mainframe that is centrally located within the vicinity of those terminals. After that, we switched toward the cloud server model, in which through and there was introduction of IP LANs and IP networking protocols, and we utilize our services and we can traverse through different networks and in order to access a particular server. And when we want more number of services, when we want to process the data in more efficient manner, then we moved on to the cloud systems. And after that, in recent years, we have switched. We have there is a concept edge computing or fog computing that's being introduced into this information system. We'll see these one by one. Okay, starting with the mainframe. Mainframe started with the range of the mainframe operation was around 1940s to 1980s. These operations were these terminals were dumb, and they don't have a processing power of its own. In order to process a particular set of instructions, we have to direct ourselves to the mainframe out there. And one more thing, there's a lot of incompatibility between the devices. For example, if we have if we have programmed a particular application on a particular mainframe, this application is not going to work on the other set of hardware uh, that's being used somewhere else. Similarly, with the start of this client server model, we used to have a set of server. We used to have a server on which will provide us a service regarding particular applications or a particular particular service is being provided by this server. So with the help of Ethernet or WLANs, we can access the network. We can access the services from the server, or we can access the databases, or we can access the services with the help of this Ethernet from this respective server. During this era, the introduction of Ethernet LANs are there. The TCP/IP protocol, introduction of TCP/IP protocol was there. So at these protocols, these rules or these applications have made has made the things easy for us. And finally, we have moved to cloud servers. Many applications, the cloud servers, we can say that it provides almost every application. Every other services are being expected from the cloud servers. In here, simply by applying for a particular service, whether the service is free or whether the service is paid, that's another issue. We can access the infrastructure out in the cloud, and we can access the services from this domain. Mostly these applications, for example, for a particular user, say here, if we have a particular user, he wants to access, or he wants to access the services from the cloud, he wants to then a virtual machine will be provided virtual machines will be provided to this client, and after utilizing this its services from the virtual machine will be handed back to the cloud infrastructure or data center. The common characteristics of this cloud computing are, firstly, they are massive. They are they are of massive scale. They are resilient computing. There is homogeneity in the environment, operating environment, geographically distributed sets. Virtualization is there. service-oriented infrastructure is there, low-cost softwares are available, and advanced security is available in cloud computing environment. The essential characteristics are on-demand self-service is there, broad network access is there, our rapid elasticity, resource pooling, and major services are there. After that, there are three types of clouds as per our utilization, or as per our demand. There are three types of clouds. One is private, dedicated for a particular enterprise or an organization. After that, we have a public cloud that's open to all, and finally, we can have a mix of two. That's hybrid cloud. Now, cloud can provide applications as per our need. There are main three applications that the main three services that are being provided by the clouds in the environment are software as a service, development as a service, and developmental creation tools. There are development as a service, after orchestration or middleware, platform as a service. In infrastructure or hardware, we can have infrastructure as a service. Similarly, we can have other services, sensing as a service, networking as a service. There are so many other services that are being provided by the cloud service as per our need, and we can utilize these services, uh, 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 and we can utilize these services in the manner or at the level of the architecture where we use them, why we want them. Similarly, there was a survey. Around 21% of public cloud was used, and around 4% of private cloud was used. Similarly, 71% of hybrid operations were used in the cloud or computing operations. And this comes around 96% of respondents are using clouds in general. Similarly, regarding the organizations, we can from the organization from the graph from the chart is clear that the left column of the graph shows different applications. Email is your uh, for small company is from the by small I that 100 employees. Uh, by medium, it's between 500 employees and you can see this scale, medium scale organizations are using most number of are utilizing most services of the cloud. Large scale organizations, because those organizations have the so now
Am I audible, Dr. Ahmed? I think there is some internet issue from your side.
Hello? Yes.
Yes. Dr. Hushmat, am I audible?
Hello.
Yes,
Yes.
yes. Who is?
The voice is breaking.
Yes, yes. There is an issue from expert side.
Yes, now you are audible.
Hushmat sir, am I audible?
You are audible now.
Actually, there is an issue from the presenter side.
Yes, presenter is not audible actually.
Yes, yes. I will just make him call him.
switch mobile data. Hmm? Is it audible? Okay, is the screen visible? Okay, let's start then. Starting with IoT can be viewed as it can be viewed as an interconnected ecosystem of uniquely addressable physical objects. These physical objects have varying degrees of sensing, processing, and actuation capabilities, and also these have the ability to communicate and interoperate through internet. Thus, IoT can be defined as you can define IoT as it's a dynamic infrastructure providing self-identifiable capabilities to the nodes, and in order to make them intelligent. And these nodes have the ability to recognize triggers in the surrounding environment and accordingly react in an appropriate manner. Thus, summing up, the IoT has two main functions: to sense the current status of the surrounding environment, and to offer tailored application specific services in response to the situation prevailing in the surroundings. So there are various applications. There are various applications of IoT, and as per IoT strategic research agenda, these applications have been broadly classified into three main domains. One is healthcare. When IoT capabilities are embedded, or when IoT capabilities are embedded in healthcare sector, we can have a lot of automated and improved services that and this then the region at the domain that's created with by enhancing the capabilities of IoT and healthcare is known as medical IoT. We can have services like real-time patient monitoring is there, automated response systems are there, medical information system is there. We can have so many other services as well. Similarly, when the IoT capabilities are combined with industry and as a manufacturing domain, then Industry 4.0 comes to the existence. In Industry 4.0, we can have services like predictive maintenance is there, logistics is there, and supply chain management is there, and so many or real-time tracking of logistics is there. Similarly, when the IoT is combined with the society or city, then smart city domains will emerge. Smart society will emerge. In this domain, we can have applications like smart home, smart grid, public safety, and monitoring. Despite having these so many applications, despite having applications almost in every sector, there are various open technical challenges or open issues that need to be addressed in order to explore the full capabilities of IoT. There are issues in standardization is one of the backbone. Standardization in both architecture and standardization in both communication technologies is the backbone for a technology. So we need to orient ourselves more towards the open standards that are built by common consensus of the things, and IoT still needs to standardize things. Okay, that's communication technologies as well. Similarly, we have architectures. Open architectures should be followed out there. And after that, availability. The availability of a service should be a must for every user, anywhere and anytime. Within the domain of the service, it should be available at any time, at anywhere, to an authorized user. And now, after this availability of availability of services to the users, routing is another issue. There are so many because routing in multi-hop mesh networks is an issue in IoT networks. Though there are various protocols that are being provided by the various researchers, like RPL is there, role is there, but these protocols have a lot of overheads, and they will all they will also be having high latency out for these routing protocols. And management and self-configuration issues are there because of the large number of devices. uh, the managing such large number of networks or devices is an issue. Similarly, these IoT devices are resource-constrained devices, and energy consumption is another issue. Another issue, because we need to have more number of computations out of this small embedded device, and that have got a limited battery out there. So high power, so efficient algorithms are required for which will require less energy or power consumption. Security and privacy challenges are there, obviously, in these small resource concentrated devices. These are some of the issues that needs to be taken care while for utilizing the full potential of IoT. Now, some of the issues that are being highlighted here can be taken care, because these are as these IoT devices are resource constrained devices having a limited processing power and limited storage. Some of the issues can be taken care by the use of cloud computing, by utilizing the service of cloud servers. Uh, so this cloud service comes as a savior to the IoT things, but there are it will to some extent it will neutralize the issues, but there are certain some issues remains are there that will remain unaddressed. See here. Uh, as we move on from the past, we have structured data that's in the form of tables out there. That's in the form of tables, SQL database, online forms, and so on. Similarly, as we move, we have another set of another type of data, that's unstructured data and numbers. That can be from social medias, blogs, click through data. And after, at present, we have image and audio system, or image and audio data surpassing these structured and unstructured data. And these may be from intelligent assistances or product IDs, or from entertainment sector or as well. But with the help with the advent of IoT, we will have the data. We have this data. We have sensed a bit of the first phase of IoT. We have data. We have sensor data. We have smart devices. We have robotic data. We have so many other data out there, and these data need to be taken care. And because of this drastic increase in the data, from the graph, you can show that there is a prediction that the data about the data that's being generated by 2025. Entertainment data is shown here, and non-entertainment data, images and videos, protective data is there, embedded data is there. You can see that around 163 zettabytes of data are being produced by 2025. That needs to be taken care of. And almost from this data, almost 30% of data is created from IoT devices. And the range of this data will be around 45 zettabytes at 2025. And this huge amount of data needs to be taken care. And now processing this large amount of data at a cloud, though cloud is an option for us, but processing this large amount of data at cloud, uh, there we require it will result in high latency. Cloud can process, one thing is there, cloud can process the data, but it requires high latency. The time that for receiving the response back is more as compared to, and then we have in the resilience impracticalities out there. We have transport costs too high, bandwidth constraints are there. There are so many issues in while sending the data, while utilizing the data or services of the cloud. Now, huge increase in total data generated, a huge increase in demand of real-time data processing. because cloud is unable to provide services to the applications that require that are time sensitive or that are real time. So processing the data at cloud end will increase the response time. In other words, we can say that it has high latency while processing the data at the network edge, while processing the data at cloud end. Similarly, we have concerns about data security and privacy. Data processing usually involves copying data from where it's stored in a database in order to perform search and other operations. By placing the data at the cloud servers, it will lead to some data security and privacy issues. As we have seen in recent years, there were data leakage from the cloud ends. For example, analyzing medical data in the hospital data center and do not copy it to the cloud. Similarly, we have accelerated chips, computer chips for AI. That's application-specific chips. That will be much more faster as compared to for processing a request of a particular node or a particular application. Rather than sending the data to the cloud, we can process it somewhere locally. And by the use of these application-specific chips, we can process the data in a much efficient manner, in a much cost as well as energy efficient manner. So, in nutshell, the number of IoT devices is going to is increasing rather exponentially, which will create large amount of data. Similarly, I have in figure here around 80 GBs of data are generated per day from Twitter. Similarly, 500 GBs of data are being generated by Boeing 757 flight per one flight. Similarly, we can have, but so sending these amounts of data to the clouds and processing it from there will have high latency and high cost as well. So also for time critical applications, for example, like in Amazon, we have every second matters, and in robotics, every millisecond matters. We can have in 1 second we can have 30 rotations out there in industrial domain. So every second matters. So utilizing services from the cloud is not an option for these time sensitive applications. Utilizing the search, for this solution, we have introduced another layer in between cloud and the sensors or IoT devices. This layer is known as edge layer or fog layer. The edge computing, this can be defined as a distributed computing topology where information processing is located close to the edge, where things and people produce and consume the data. In other words, edge cloud is an optimization of cloud to move the computation and storage close to the network edge. That means we will have move this computation and storage. We will provide these facilities, though in a limited manner, closer to these devices. Edge computing does not replace cloud computing. It's not a replacement of cloud computing, but much information processing will continue to be done on cloud data centers. Processing at edge will focus on functions in which it's important to avoid latency and to avoid data transfer to other reasons like privacy and security. Processing, for example, business analytics that requires large amounts of heterogeneous data will stay in the cloud. Also, in here, you may also be familiar with the term fog computing. Fog computing is a subset of edge computing. It's a decentralized architecture in which data, compute, storage, and applications are located somewhere between the data source and the cloud. See, from the figure, see here, we have three levels. In our network system. We have access level. We have access level. This is our access level. This is our distribution level, and this is our core level. So by placing a limited source of by placing a limited resource unit in at the edge of the network. Say one hop away from the gateway, we can say that it's at the edge of the network. So this is known as edge computing. These devices are known as edge devices. Similarly, by placing these same units in between cloud and devices, and between these edge and cloud, sorry, in here, it can be here, it can be here, it can be somewhere here, closer to the user, closer to the IoT devices. This consortium is known as FOG. This was firstly introduced by the two researchers from Cisco, and they have introduced this concept of fog computing. The benefits of using fog computing obviously is it benefits in minimize the network congestion, minimize the end-to-end latency. It handles the connectivity bottlenecks, improves the security and privacy of the data. So a paradigm that extends cloud computing and services to the edge of the network, similar to the cloud, fog provides data computation and storage and application services to the end users. In other words, we can say that okay, fog is a subset of edge computing, and so these two terms, edge computing and fog computing, are used interchangeably in industry. More simplified view of architecture, fog computing is a system level architecture to extend computation, network, and storage capabilities of the cloud to the edge of the network. That means providing these things closer to these devices, to these IoT devices. Now, three-level architecture of edge computing. We can have three-level architectures. We can have in the first level, one is front-end layer, second is near-end, and third one is far-end layer. The front end comprises of the IoT device or nodes that are placed in vicinity to the environment or in the environment for sensing purposes or for activation purposes. Similarly, the data from these devices are transmitted to the higher levels, that's to near level and far level, as per the need. The near end devices are much powerful devices as compared to these front-end devices, and they have more number of processing power. They have more processing power, storage, etc. And these are known as edge nodes or edge servers. Similarly, we have far end. Cloud servers comes to the far end, or data centers comes to the far end of the this architecture. Okay. From the past, there is a shift. There is an increase in data. This is a survey conducted by Cisco. It predicts that there is a 3-time increase in data traffic to data center. That there is 3-time increase in data traffic to the data centers, and 31% of the inter data center traffic grows, and 37% of these data that's being transmitted to the data centers are being processed by edge servers. Now, edge server, what are the benefits of using this edge server? It will provide us with the low latency, real-time support to real-time operations, optimize infrastructure, and rapid response. It will help us massive various data storage and movements and data sovereignty, enhance security and privacy. Obviously, it will help us in context-aware routing, as well as context and location awareness or localization. It will help multi-access networking across large-scale and small-scale sites. These sites that are unreliable, limited, or using high bandwidth, are demanding high bandwidth, and it can provide intelligence and smartness and autonomy at the edge of the network. So this service handling environment is like if a particular IoT node is utilizing a service, it can utilize a service from the fog end or the cloud or the edge end or the edge layer or the fog layer. Similarly, if this layer is unable to service provide the service, or we require the services. For example, for business analytics, the data will be transferred to the cloud end, and we will and it will get with services done from the cloud side. Now, cloud servers in here, like we can have different flows of traffic. We can have flow of traffic from the IoT nodes to the to the fog layer, and similarly we can have traffic from fog layer to the cloud layer. The traffic from here to the cloud servers, or the traffic from cloud server to the IoT layer. Similarly, these traffics. One is north and south. These traffics. From fog to cloud or cloud to fog layer is known as north flows, and similarly from fog to this IoT device, these are known as south flows. There can also be exchange of information or exchange of traffic between the different fog nodes. This is being done by east and west. This is being labeled by east and west flows. This is the general components of fog computing platform. We can have different nodes, IoT devices, either passive or smart. They can utilize services, different services. We can have platform services. We have APIs we have virtualization environments. We have hardware. So on these, this is the hardware infrastructure of the cloud of the fog level. Similarly, we have different virtualization softwares out there and we have features like load balancer is there, virtual machine scheduling is there, network management is there, system monitoring is there. With the help of APIs, we can provide services. We can interact with the other. Cloud cloud layer, as well as with the help to the other devices which are utilizing the services of the fog layer. We have authentication mechanism and authorization mechanism. We have service management. We have cloud agents. We have offloading mechanism management. We have location awareness services or context aware services. We have communication services as well. And on the top of it, we have application and virtual machine application running on different virtual machines that are being provided to the different users. Now, pushing intelligence up towards the cloud. Cloud challenges are critical latency requirements are there. So this challenge is being held by fewer network hops by providing the fog layer in between that's close to the devices. Similarly, we have data-rich mobility, data locality, and data local caches are maintained in the edge servers. Geographic diversity is there. Intelligence localized as appropriate. The network bandwidth limit is there. Local processing is there, and less core that will require less network loads. Reliability and robustness is there, but here we have fast failovers, local repository in emergency. We have analytical challenge, analytical and storage at the right time. User data and geo privacy. Fog can aggregate user data. Similarly, we can push intelligence down towards the endpoints. Endpoint physical constraints are energy, because these are limited devices. They have a limited number of resource constraints. They have limited power. They have limited space, and they are very close to the environment. That means they will face issues like temperature, high temperatures, humidity, vibrations, etc. In this, fog can replace this thing by fog nodes can be more energy, can have more energy. So this. By sending the data to the fog, and getting the response in appropriate response or appropriate information, we can conserve the energy. Similarly, we have fog nodes can be physically larger as compared to these nodes. Better cooling systems are there in fog nodes. Endpoint functionalities, constraints, processor throughput is there, storage capacity is limited, reliability and modularity. And endpoint security constraints are there in the IoT devices. Similarly, we have terabyte to petabyte storage capacity is there. Fog capabilities can be more redundant. Modules can be added as needed to the fog network. Fog has a better physical and network security as compared to the IoT devices. So we have IoT with fog. If we utilize fog layer for providing your services to these IoT devices, we can simply connect any protocol or device through an open platform, use bandwidth and storage capacity more efficiently, sending only relevant data to the cloud. That means we can filter out data, we can aggregate data or classify the data at this layer, and send more appropriate data to the upper layers. That's the cloud servers for analysis. Analyze at this level, we can analyze and act at the right data at the network edge. So in general, we can have different IoT devices, uh, a mesh of a complex mesh of or network of IoT devices that are resource concentrated devices. These resource concentrated devices are utilizing the services of the distributed in a distributed environment at the edge of the network or closer to the edge of the network, and with the help of core networks we can simply reach to the data centers in case of large processing or in case of business analytical informations out there, and we can provide services applications from these analytics in different areas. So the point to discuss this slide is that as we move from this layer, IoT layer, to this data layer, we will see that there is an increase data volume from the edge to core, data refinement at each layer. There is a refinement of data at each layer, because it will define the data, it will classify the data, or it will send the data required amount of data to the cloud, and rest it will process the data here over here. Similarly, if we see in contrary to this data, if we see the analytical algorithms, so more complex algorithms will be run here, and lesser complex or similar algorithms will be operated at edge. So movement of the data from the fog to cloud, we can have different data as this is, if we consider this as an IoT layer. Obviously, it will have large volumes of data, wide variety of data, high velocity of data generation, and these data units are being handled by using different rules or policies, and these data are classified. This data is being classified as per these different rules, patterns, or actions are being taken, and these are sent to the cloud servers, and in response to this data, the information is acquired from the data from the cloud servers, and it's being displayed to the IoT devices. By utilizing the services of fog here, data reduction can be possible. Control responses there, data virtualization and standardization is there. Now, if we compare the requirements of cloud and fog, latency in cloud is high, and as well as in fog it's low. The jitter is high, and in fog computing is low. Location of servers is within the internet, and at the edge, its server is located at the edge or close to the edge of the network. Distance between the client and server is multi-hop. It's one hop distance in fog computing, whether it be mobile edge computing, whether it be cloudlets, whether it be fog layer, it's one hop distance. Security varies among different cloud providers, but it can be provided at this fog layer as well in a customized manner. The attacks on data on fly. Yes, Jhangi sir. Same issue. बेशक पहुंच गया 18 बस कर कहाँ कर सोच पे देखिए बात Hello, Jhangi sir. Hello, Jhangi sir. Jhangi sir. Jhangi sir. Hello. Jahangir. 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 Am I audible?
Am I audible?
Jahangir. Yes, you are. Jahangir.
Audible, sir.
Your voice is not audible. Am I audible?
You are audible.
Audible, sir. Audible.
Yes, no minute. Jahangir. Jahangir.
Audible.
Jahangir. Okay. Am I audible now?
Yes, you are audible, sir. Audible.
Okay. Okay. Yes. Okay. Okay, by comparing these
Once
two.
again, Hushmat.
Yes. Jahangir. Jahangir. Okay. We are comparing the services or the features requirements of cloud computing and fog computing. Normally, we have the cloud servers are centralized located, while the fog servers are distributed in manner in the form of mobile edge nodes in the form of cloudlets. They are distributed in the environment as per the application. Number of servers or nodes. Obviously, we have data centers, and for fog, we need to look at distributed processing of information. We are with the large nodes. Support for mobility is limited to the in cloud environment, but for fog layers, it provides us with the features of context aware routing and context aware application services. So it's supported in fog layer. Similarly, we have real-time interactions. These real-time, the support for the real-time applications or time-constrained applications are lesser in cloud computing. While contrary to this thing, we have got a good support of for time, real-time or time-sensitive applications in for computing environment. We can also access the fog computing services with wireless. medium. Similarly, there are some use cases for edge computing where edge computing can be helpful in providing the services different in different areas. I have mentioned a few. Say, for example, if we feel or if we presume if we feel a delay in when we are talking to Alexa or we are talking to some other intelligent robot, if we feel a delay, virtual assistant, if we feel a delay, it's not an issue. But in automated self-driven cars or in automated systems, if there is an issue, if there is a lag in the network or if there is a lag in the decision making or information response received from the upper layers, in that manner, it would be an issue. Similarly, by utilizing the service of edge computing in the domains of different domains, we can have smart buildings, which includes obviously our homes, factories, warehouses, hospitals, etc. We can have smart manufacturing domain, that's Industry 4.0. We can have the features like predictive and proactive maintenance is there, real-time tracking is there. We can have self-driving cars, drones, airplanes, systems, etc. We can have connected car services. We can have augmented support for mobile augmented realities. That the support for this service is not present in cloud computing. We can have networked games. We can have mobile e-commerce. We can have numerous services that in healthcare domains. We can have wearable devices. We can have robot assisted surgery. We can have medical data analysis in the hospital. We can have in earlier cases there was a experiment or a project which involved two companies, NASA and Intel. They were trying to build this robot assisted surgery by utilizing the services of the satellite. So that project, the result of the outcome of that project is that the latency while utilizing the services from the satellite is very large. So while utilizing, they have repeated the same experiment with the help of edge computers as servers out there, and it has given us good results. We can have robot assisted surgeries while utilizing the service from the edge servers. We can have physical security and surveillance systems. We can have energy systems, for example, smart grids is there, SCADA systems are there. Some telemedicine and agricultural system controls are being enhanced by using IoT systems. We can have improved virtual assistants, like Alexa. Similarly, we require all the three layers by giving in nutshell. We can IoTs are limited resource control devices, and these devices are very close to the environment, and they can be both static and can be mobile. Similarly, we have edge servers. They are distributed, having large power in large capacity in terms of computing power, storage, and they while utilizing the services from this layer, we will experience a faster response time, and they provide support for time-sensitive applications. And these servers can be static, and sometimes they can be mobile as well. But in cloud servers, they are centralized, having very large resources in terms of the both processing power, storage, but they are static in nature. And lastly, there are various projects done by different organizations for implementing edge computing for different applications. They have used different approaches. For example, Acarneo is there. It has used various it has used OpenStack and Kubernetes for implementing edge servers. And similarly, this project has been done by different participants like AT&T is there, Intel is there, ARM is there, Nokia, Ericsson, and so many other organizations are funding this project. Similarly, we have Starlink, we have Airstrip, we have Cord, we have VCO, we have EdgeX Foundry, we have OpenEdge, we have CubeEdge, we have Azure IoT, we have IOFog, we have Ellipse Cura. Some of these use the loosely coupled services, microservices. Some of the projects have used for management purpose. They have used software-defined networking, which will slice out networking management features. Like we can have a plane in which we can simply configure the devices out there, and other plane or the data plane that will simply transfer the data packets as per the policies that have been provided to these that have been framed in the control plane. So in that manner, managing that by utilizing software-defined networking facilities, we can manage we can manage the resources, we can frame the policies, we can have efficient routing schemes in the IT environment. They people have implemented some of these projects have implemented this feature into their edge while implementing their edge platform. So every other feature every other project every project was built with a particular target in mind to provide provide particular features. For example, some are good with latency, some are good with data analytics, some are good with some other features. So utilizing these services or providing these services uh, in a different manner. But for us, edge computing implementations have difference in the characteristics. Use cases have their own unique features and suitable implementations. Project could be categorized into different implementations. For us, finding the features of your use case and choose the most appropriate implementation for that is the main choice that you have to build. So that's all. Hope this is clear to you guys. And if there is any question regarding this fog IoT environment, you can ask. Yes, Jahangir. Jahangir.
Am I audible?
Yes, you are audible. I hope
Okay.
it's clear to everyone.
Audible.
Yes, Jahangir.
Am I audible?
Yes, you are audible. I hope it's clear to everyone, and I will stop here. Thank you for listening patiently and attentively. Thank you.
Actually, we are also facing same issue of internet shutdown from whole in the whole institute right now. So
Yes,
I have connected my mobile data right now with this system.
yes.
I am not able to at least
Okay, no issues. Thank you.
audio quality of my laptop is a bit very low. That's I am not able to at least hear from the speaker. So among the participants, if you have any query or any sort of question, you can ask directly to the expert.
Okay. I hope it's clear to everyone.
There are no questions, huh?
Okay, thank you. Can I sign up, sir?
Yeah.
Thank you. Thanks a lot.
What about the security issues? Okay.
Yes. Sir, is there any question for me? You are not very audible. With the rest of the guys, am I audible? Okay.
Sir, your voice.
Regarding
Yes, sir,
regarding
audible.
security concerns, Edge and fog layer provides a very efficient security mechanism. Though because of the limited constrained nature of the devices, IoT devices, we have we can't implement high-end security protocols algorithms out there because they have limited battery power and they have limited computations. By sending the data at the edge of the network, that means it will remain with the organization, and we don't we can if we have to transmit the data to the further to the internet or to the exteriors of the network, we can simply make an encryption to this data and send it to the in a more appropriate manner. In other sense, we can for the more appropriate or sensitive data, we can process it locally using our edge computers or the fog layer devices. We can process it in the neighborhood or in the neighboring fog nodes as well. In this manner, we can have much better security for cyber physical systems regarding IoTs.
Thank you very much, sir.
Thank you.
I think, am I audible?
Yes, sir.
Okay. Okay, great. I think we have now completed this session. I thought they have completed it. There were the 2 sessions. I think the expert Dr. Hushmat has completed in. So we are done with for today's session. We will join once again on the next day. I hope. Hello. Just a minute. I will connect. Still, do you have any query regarding to the present sessions which we have completed till date? Okay. Could we shift to Zoom or Google Meet? Yeah. Basically, we have in our institute we have purchased Cisco WebEx, so we have to use Cisco WebEx. At times there may be an issue with the internet connectivity from the experts, and but we will try our best to sort out these issues as soon as possible. I think there will be no more sessions for the day. So we have concluded this. So we will meet inshallah tomorrow. So you can leave now.